Okay, so for those of you listening and watching online, we've decided that today's revision seminar will be about subspaces of Rn and basis as well. And I'm going to talk through how I think about those things and organise it in a slightly different way to the way you learned it, because if you organise it in this way, it might be a little easier to remember things. Okay, so before I even get to subspaces, I do just want to mention a couple of things that if you've ever talked to me about this before, you would have heard, but I need you to know. So, let me just talk about vectors generally. And let me zoom in so that it's easier to read. Okay. So, the reason we have to talk about vectors is because subspaces are created from vectors. Whenever we learn about any object in maths, we need to ask several questions about it, which are: what is it? What can I do to it? And what can I do with it? Because subspaces are made of vectors, we need to know about vectors first and ask those questions, because subspaces is one of the things that you make with vectors. Okay, so that's just the reasoning behind it. So, to a mathematician, a vector is a point, not an arrow. Okay, that's a really important thing to remember, that most of the time when a mathematician talks about a vector, what they mean is a point. Okay, so just as an example, that's a vector to a mathematician. It's something that has three coordinates. It's just a list of three coordinates, and those coordinates are numbers. And since those numbers are in the real numbers, we have that we're making it from the real numbers, and there are three coordinates, so it's R3. Okay, so when we say R3, it means vectors with three coordinates, with the coordinates chosen from R. When we say R7, it's vectors with 7 coordinates, with the coordinates chosen from R. It is technically possible to say something like Z3, which is saying that 3 coordinates, but the coordinates are chosen from the integers. Okay, it's possible to do that. So this is not in Z3, it's in Q3 actually, but it's in particular in R3. So we don't talk about the other ones in Maths 1A, but they're there if you wanted to make them. Okay, that's what vectors are. To a mathematician, they are just simply lists of coordinates. Okay, and this list of coordinates can represent a point in space with an x coordinate 5 and y coordinate -1 and z coordinate 2/3. It could represent, if I wanted it to, it could represent an arrow that goes 5 along the x, -1 along the y, and 2/3 along the z, and that arrow could be placed anywhere we like. And simultaneously, it could be either one of them depending on what we wanted to do with it. And mathematicians do not distinguish which one they want you to think about it as at any given moment. So you're going to have to make that up at the time. And most of the time, it's a point. In fact, it becomes an arrow when we want to do things to it, like adding and multiplying by stuff. Okay. So just as a picture, if I talk about this point and this point in R2, then if I want to add them together as objects, then I have to think about them as arrows. So I have to go, oh well, this one is that arrow, and this one is that arrow, and then what you normally do is you shift one of them to be at the other end of the other one, and you make a new point there. So this is the point U, this is the point V, and this would be the point U plus V. So, but unless we're actually adding them, they're points. Okay, we only think of them as arrows if we're adding them and multiplying them by scalars. And it's actually almost as if there's this diagram and the diagram with the arrows actually lives in another place. Okay, so here on this picture they're points, and then I can draw them as arrows elsewhere and then bring it back later. Okay, so I'm going to talk a little more about that in just a moment. Now before I have this done, I could say that it could be just a column matrix as well. And I know that sounds strange to say that that's different somehow from the list of coordinates above, but it is, because a matrix is an object in its own right that does its own maths. Okay, so if I think of it as a matrix, then the maths will behave in certain ways, but if I think about it as an arrow, then the maths will behave in certain ways. Okay, so I need to be able to convert it to a column matrix at any moment. And I should say that vectors, unless otherwise stated, are always columns. Okay, so unless they state otherwise, vectors are supposed to be columns. They'll be a bit sloppy when they write it like this, because when you're just thinking about R3, it's just a list of coordinates and it doesn't matter whether you write it as a row or a column. But if you're going to make it interact with a matrix at any point, it has to be a column. At least for the purposes of what we're trying to achieve here. Okay, so I can add to this like represented as. Okay. So it's almost as if these are just representations of the vector, and the vector is some sort of esoteric object in its own right, and these are just ways that we have of looking at it. I do want to make a point about addition. Adding vectors can be thought of in multiple different ways, and it's useful to be able to think about it in all of them. I've already done one of them where they're both arrows that start at the origin, and we add them head to tail to get a new point, to get a new arrow technically that goes from here, like that. But it is possible to think of them, one of them as a point and the other one as an arrow. So if I do this, I'll do it in, that doesn't matter. Yeah, I'll do it in 2D. Something like that, 1, 5 plus 3, 2. I could represent that if I wanted to, like this, as here is the point 1, 5. And from that point, I go an arrow 3, 2, so I can go 3 this way and 2 that way, and this is 3, 2. And then the result is this brand new point here. Okay, so I can actually think of it as a point plus a direction. So this is a starting point plus a direction. So it's almost as if, just going to see if I can make that better focused. Okay. It's almost as if you simultaneously in that addition think of one as a point and the other as an arrow. And that's a really useful way of thinking about things, because that means I could think about, say, this as saying, well, if I've got all these different options for what t could be, each of those would produce a different point. So I could do my 1, 5 like that, and if t was 1, I would go this far, whoops, that far. I would go that far, and I would get this point. And if t was 2, then I'd go twice as far, and I would get this point. And if t was minus 1, I would go in the opposite direction and get this point. And if t was minus 2, I would go in the opposite direction and go twice as far and get this point. And if t was a half, I would get this point. And if t was minus a third, I would get this point. And so if I use all the possible values of t, what I will do is I will fill out a line. And I'll get an entire infinite line that starts at that point 1, 5. So if you do point plus t of coordinates, what you'll do, if you do coordinates plus t of coordinates, what you're doing here, this is a starting point. And this is a direction. So just so that you can get a handle on this switching between directions and points. Okay, and the result of this, for each value of t, the result is a new point. Okay? So it's usually like x, y. And this is my new point. Up here, this new point was 4, 7, and that's my new point. And that is why if you want to know the direction vector that goes from one point to another, you should subtract them. Because if I want to know the direction, I should do my new point minus my start point just in terms of the maths. I should go subtract this from both sides and ta-da, there it is. Okay. So that's really important information. And that means that when we see this at any point, we can say, if I collect all those points, those coordinates together as points, then what they make is a line. Okay. So before we finish talking about vectors, I do want to talk about sets. So, a set is the most fundamental of all mathematical things. So a set, and that means that we have to define it in terms of other vague words because it's really basic. Okay, there's nothing below it. So a set is a collection of objects for which there is a rule for telling whether the object is in the set or not in the set. That is the fundamental property of a set. There is a rule for telling whether things are in or out. Okay, so a rule for being in or out. So at any point where it mentions anywhere in your notes that something is a set, for example, a convex set, or a subspace, that's a kind of set as well, it's just a collection of points, usually, where there is a rule for being in or out. So at any time a set is mentioned, you should ask yourself, what is the rule for being in or out of this set? Okay? And so what you imagine is, if you find all of the points that satisfy the rule for being in and you colour them in, then that new object is the set. Okay. So you can make sets in any way you like. And there are three major ways of making sets that I would like to point out. So, let me just think. No, there's four. There are four ways to make sets. Okay? So the first way is to just list all the things that are in the set. And the rule for being in or out is that if it's in the list, it's in, and if it's not in the list, it's not in, like it's out. So way number one is list all of them. We'll do them as vectors, i.e. points. Okay? And so your rule is in the list means in the set. Not in the list means not in the set. That's fairly basic, okay? Okay, so for example, that is a set that's constructed by just listing the things that are in the set. The things that are in this set are the vector 103, the vector 001, and the vector 112. That is all the things in the set, there is nothing else in the set. So I can say, I know this is really basic, but I can say, I should give the set a name. Let's call it S for set, equals that. So I can say that 103 is in S, that's what that symbol means. So it is an object which is part of S, since it's in the list, right? And I can say that the vector 111 is not in S, since it's not in the list. If I create this set in 3D space by colouring in the points that are in it, all I will get is 3 dots. A dot for 103, a dot for 001, and a dot for 112. That is all there will be, 3 separate dots. If I actually drew this set. Because you know you can always draw them. Okay. So the second way to make sets is a bit like listing all the vectors that are in it, but there might be infinitely many vectors in it, so you need a way of listing them in a way that you can have infinitely many. So it is possible to have like a comma dot 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 as long as you can understand the pattern. But there's another way, it's like listing all the sets, but it's to have a rule for how to construct all the things in the set, you know. So show how to make the vectors. So your classic example, so this time it'll have the curly brackets which tells you that it's supposed to be a set, and then it'll have this vertical line, okay? And this time the really important part of the rule that tells you whether it's in a set is going to be this bit. This is going to be my rule, okay? And this part here is just going to give you further details so that you understand how to use the rule. Okay? So, an example is something like this. Like that. That is a rule for how to make things that are in this set. And any variable that you mention in that, in the second part, you have to say what it means. So it's something like, you know, T in R. Okay? So, this set, we know already this is a line. If I drew all of these points and coloured them all in, what I would produce is a line. So we know that what this set looks like as an object in space. Our question is, how does the rule work? So this rule is telling me that I can make all of the points in this set by choosing values of t. I'm allowed to choose any t I want, and it's in R. And if I choose all the t's and find all of the answers to this, that will produce the whole set. Okay, so if I want to ask this question, you know, 2, 2, 4. 2, 2, 4 is in the set because 2, 2, 4 is actually equal to 1, 2, 3 plus 1 times 1, 0, 1. Okay? It's in the set because it's possible to construct it by that process. I was able to construct this point by doing this process for an appropriate t that is okay based on the rules, and therefore it's in the set. It's really hard to tell if a random vector is in this set. Okay? So, let me just do the next part of the example. Oh, that's okay. Just a second. This is an A3 piece of paper. Right. I'll just keep the set rule in view. This is the answer to this question is going to be no, but I just wanted to point it out. I'm going to ask it as a question. So is 2, 2, 3 in my set? Okay, that's my question. Okay, so the only way to know if it was in the set would be that if it was written like this. So the only way to tell for sure would be to say, well, if it was, then 2, 2, 3 would be equal to 1, 2, 3 plus t of 1, 0, 1 for some t, which would mean that using the first coordinate, 2 would have to be 1 plus t, which would mean that t would have to be 1. So using the first coordinate, I can say that the first coordinate here must be equal to the total first coordinate here. So I've got 1 plus t in the first coordinate of that one. And so t would have to be 1. But if t was 1, well, I could just do it from each coordinate, right? The second coordinate would have to be 2 plus 0t, which doesn't tell me anything about t, so that's okay. That one's fine. And the third coordinate would have to be 3, which would be 3 plus 1t, which would mean that t would have to be 0, and it can't be both 0 and 1 simultaneously, so there's no solution. No solution for t, so therefore it can't be written this way, and therefore it's not in S. Okay. What I want to point out, and I'll point out again in a minute, is that a set that's like this, it's really easy to make points in that set. If I asked you, give me 10 points in that set, you just choose 10 different values of t and figure out what the point comes out to, and there they are. Okay, so I could choose t equals 0 and get 1, 2, 3. I could choose t equals 1 and get 2, 2, 4, and I could choose t equals 2 and get 3, 2, 5, and I could list them as long as I wanted to. But if you gave me a random point and said, is it in this set, it's actually quite difficult to decide. Okay. My third way of making sets, this will all relate to subspaces extremely well soon, so I just need to say it first. My third way of making sets is to have a formula, an equation, or some sort of rule, an equation that you have to sub things into in order to tell. Have an equation to satisfy. So this kind of set will have the tendency, it will look the same superficially to the other one. It will have the curly brackets and it will have a bar in the middle, or sometimes a colon. Some people write that as the two dots on top of each other, a colon, punctuation mark. Though that seems to be passing out of fashion because it's easy to mistake a colon for just a fly speck that happened to happen because of your photocopier, but a vertical line's easier to see. So it'll look like this, and in this case, it's this part that's the rule. Okay? So what the first part will do is it will set up your variables so that you know how to deal with them. So it'll usually say something like, x, y, z in R3. So this is saying, where should I look for points? It's just orienting you to where this set belongs overall. And then it will have a rule something like, something like that, x plus 2y minus z equals 1. Let's write my z point here. Okay. But any rule could do. It could be x squared plus y squared equals 4. It could be, anything. Okay, as long as there's something that some sort of equation that you can put there. That's how this type of set is made. And the way that you tell if things are in this set is to sub it into the formula, and if it works, then it's in the set, and if it doesn't, then it's not. So I should have written that back here. Just a second. So my rule is here for the old set. If you can make it this way, then it's in the set. But if you can't, then it's not. I'm very sorry, but you must understand that if you're going to make up a revision seminar on the spot based on what people ask you today, you're going to have to go back and change it every so often. So that's why I'm going to put this online afterwards. So if you can make it this way, then it's in the set, and if you can't, then it's not. So I may even write my notes out again so that they're prettier. Okay. But for this set that we're just making now, if the point satisfies the equation, then it's in the set. And if the point doesn't satisfy, then it's not in the set. Okay, that's my rule. Okay? Every set that you see, you need to go, how do I tell if things are in, how do I tell if things are out? So it's really easy to ask the question, is this point in the set? Okay, so if I had my point and I said, is the point 1, 1, 3 in S? Then I could go, well, I'll just sub it into the equation and see if it works. So 1 plus 2 times 1 minus 3, I put the 1, 1, 3 in for x, y, z. This comes out to 1 plus 2 minus 3, which is 0. So no, it's not in the set, because if it was in the set, it would come out to 1. Because this says that every point in the set, if I sub it into the equation, will come out to 1. Is 1, 1, 2 in the set? Well, let's see. 1 plus 2 times 1 minus 2 is in fact equal to 1, so yes, it is in the set. That's a tick, by the way. Let us make it look more like a tick by drawing it in green. And just to make it even more like kindy. Okay. All right. So it's really easy to tell if points are in this set because I just sub it into the equation, and if it works, it's in, and if it doesn't, it's not. The hard part with this set is to say, well, you know, is a random point in it? Like, not is it in there, sorry. Can you tell me a point that's in this set? So what if I wanted to find a point that actually is in S? I mean, obviously I already have one of them, 1, 1, 2. But what if I was just randomly given S and I was asked to find a point that was in there? Well, one method would be to pick a point, just pick any point, and just keep trying points in the equation until you get one that works. And possibly once you pick one, sort of adjust the last coordinate until it does fit. And the other way would be to sort of know that this equation's got 3 unknowns, so if I pick 2 of them, it should be possible to figure out the other one. So pick sort of x equals 1 and y equals, or even better, x equals 0 and y equals 0, because they're really simple. And then 0 plus 2 times 0 minus z would have to be 1. That would mean that z would be minus 1. So therefore, the point 0, 0, minus 1 is in S. I can make a point like that, but I have to do a bit of work. And you can imagine if there was a list of equations that I had to satisfy all simultaneously, then it would be quite difficult to do that, to make points that were in the set. All right, so here I'm going to say something. In Maths 1A, the whole point of most of what you're being told about subspaces is to convert a subspace whose definition looks like this into a subspace whose definition looks like this. You want to turn it into an equation version, from the equation version to the how to make points version. That's what you're trying to achieve when you're making a basis. So, yep.
X equal 1 and y equal 2 or something.
I would make a different point entirely. So that was a good point. So I could say, you know, pick x equals 1 and y equals 2, then 1 plus 2 times 2 minus z would have to be 1, and so I'd get 5 minus z has to be 1. Whoa. And so z would have to be 4. And so therefore the point 1, 2, 4 is in the set. Okay, so you can, if you pick 2 of the coordinates, you should be able to figure out the last one. Now that's only going to be true if they've only got one equation. But it does give you a method for finding points that are in sets. Okay, let's just keep track of the ones I've actually done today. So I did say that there were 4 methods of finding sets. Method 4 is to construct it from other sets. So in calculus, right near the beginning, you actually saw this in some of the tutes. where you constructed sets on the number line from other sets, and it's the same thing. You can construct sets from other sets, so I could always say, you know, S is a set which has its own rule, whatever it is, and T is a set which has its own rule, and then I could create a new set, S intersection T, for example. And so what you'd need to do is you need to somehow combine the rules for S and T together to have a new rule, and to be in this set, so the rule for S intersection T is that if you're in both S and T, then you're in the set. But if you're not in both, so you could be in one but not the other, so not in both means you're not in the set. Okay, the classic picture is a Venn diagram that sort of goes like this. You know, you've got your S and you've got your T, and this bit right in the middle here, that bit there, that's S intersection T. Okay, the bit that they share. But you could also make new sets this way. My new set S union T, and the rule for that is if in S or T or both, then you're in the set, but if in neither, then you're not in the set. And the classic example of that so there's my orange set and my blue set. All of this together that's S union T. Okay? So my green is S union T. All of it. So if you think about it, it's the set gluing operation. You glue the sets together and you make a new set. Okay, that's what union is. Whereas intersection, you chop the sets off, you chop off the bits you don't want, and you're left with a bit in the middle. So in my characteristic style of coming up with crazy ways of remembering things, union is like a bucket. You get all the points in both and you chuck them in the bucket, and now we have a new thing that everything's in the bucket together. Or let's think of it as a cup, like this. Put everything in the cup. If we turn the cup up the other way, then we can use it as a scone cutter and chop off the bit in the middle. Okay, which is why it's up this way, right? Because we're cutting off the bit in the middle. Okay. Some people like that. That makes me happy. Okay. There is one more rule it's worth mentioning, but you don't usually use it for subspaces. S without T. I should put the words on here. Just a second. This was intersection. That symbol is intersection. And this one was union. And this one is read aloud as without. So the new set S without T is literally S without T. So it will be, the rule will be, you have to be, if you're in S, you have to be in S, but not in T, then you're in this new set. And if you're in any situation other than that, then you're not, okay? So if you're not in S, or you're in T, either one of them, doesn't matter which one, or in T, then you're not in the set. So in terms of my pictures, if this one's S and this one's T, then I take S and I chop off the bit that's in T. So that green bit is S without T. Not that we use that in subspaces, but it's good to know because you can use it in calculus. Okay, so there are my 4 ways of making new sets. Okay, the last one is the most complicated, and it uses sort of algebra in terms of the algebra in the sense of writing symbols. And the most important ones for subspaces are the middle 2. Okay. So the most important rules for subspaces are the middle 2, the ones where you construct it, set construction, or where there's an equation. Okay, either one of those, they're really important for subspaces. And now I can finally talk about subspaces, now that I've oriented you. So let's just make sure we've got this right. Vectors. Just a second. My pages are out of order, so I just want to make sure that I put them back in the right order. Right. So vectors can be points or arrows. I can use them to make new points. I can imagine them as points and arrows freely, as much as, flip between them as often as I like. And I know that using a point and a direction, and I multiply that direction by stuff, I can make a line. And I can also make sets by doing a construction like that, or by equations and a couple of other methods. So the reason I need to talk about all those is because both sets and vectors are what subspaces are made of. Okay, however, while I'm at it, because people keep asking me, there is something interesting you can say about vectors, which is whether they're linearly independent or not. Okay, and so while I was talking about vectors, I'm just going to add this page in back there. Vectors can be linearly independent or linearly dependent. So this is something that you can say about vectors. Okay, and you don't say it about subspaces or sets, you say it about vectors. Okay, so that's the other question you can ask when you make objects. So you can say, what is it? You can say, what can I do to it and what can I do with it? The other thing you can ask is, what can I say about it? And I could say about a collection of vectors, is the collection linearly independent? And note that it's not any one vector that's linearly independent, but that phrase belongs to the whole collection of them, okay, the set, as it were. Okay, so this linearly independent is saying, well, it's not just vectors, it's a list of vectors. Lists of vectors can be linearly independent. Okay, now, what this relates to is how mathematicians think about vectors. To a mathematician, I said a vector was a list of coordinates. That's not strictly true. To a mathematician, a set of vectors is a set of objects which I can add and multiply by scalars. That's all a vector is to a mathematician. So if I wanted to, I could treat matrices as vectors because I can add them and I can multiply them by scalars. I could treat functions as vectors and because I can add them and multiply them by scalars. At a pinch, I could treat equations as vectors too. Okay, so I could treat all sorts of things as vectors, but it all boils down eventually is that it's possible, if no matter what object I pick as a vector, it's usually possible to describe it in terms of coordinates if I want to. And so therefore I think about it in terms of coordinates. And so those key operations of addition and scalar multiplication are really important to mathematicians because that's what tells you that it really is vectors, because it's okay to do addition and scalar multiplication. Okay, and so linearly independent is a property all about addition and scalar multiplication. So if I take, I'm sorry, I'm just going to scrap that page. What can I do with vectors? I can make linear combinations. A linear combination is doing addition and scalar multiplication simultaneously. Okay, so basically, this is the definition of linear combination. If U is something of V1 and something of V2 and something of Vk, then U is a linear combination of V1 up to Vk. That's the definition of what linear combination is. It's a terminology. It's not really a thing, it's just a terminology. And so the idea is that this is a linear combination, but also whatever that works out to, that answer is called a linear combination as well. Okay? So it's both a process and the result of the process. In the same way that you could say that sum is a process, but you can also talk about 7 being the sum of some other numbers. So you can say that this is a linear combination of these other vectors. And so all we've done is we've multiplied them all by some scalars. We might not have multiplied any of them. It doesn't matter, the scalar is allowed to be 1, it's allowed to be 0, and I've just added the results together and I've got this new vector and it's called a linear combination. And that is the whole thing that vectors do. Vectors do linear combinations in a really consistent and basically interesting way. So I can go actually uninteresting way. We can say, yep, they do what they're supposed to do. I can expand brackets, I can do the addition in whatever order I like, it all works fine. Okay, that's great. Okay, and you should know what happens to vectors when you do linear combinations, and you should also know what happens when you produce all the linear combinations, but I'm going to get to that in a minute. So, that means that about vectors I can say if they are linearly independent or not. Okay, so about some vectors I can say if they are linearly independent or not. And it's all to do with the linear combinations. And there is a definition, and there are a whole lot of other things that you can look for to tell if it is or it isn't without having to use the definition, which is really important. Okay, so the definition is this. So V1 up to Vk as a list together are linearly independent when this equation only has the solution that all the a's have to be 0. You know, is only possible if A1 is 0, all the way up to AK is 0. That's one way of saying it. The other way of saying it is to say that has only the trivial solution. So I could at this stage have said, you know, is only possible if, you know, or has only trivial solution. Okay? That's the definition. If you're ever asked what the definition of linearly independent is, well, that's what it is. The reason, now there are many things we could have chosen to be the definition of linearly independent, and we choose that one because it matches with using matrices, and matrices are helpful in this setting, okay? So that's the definition. There are a list of other things that tell you whether it is or not without having to directly use the definition. So, things that tell you that they're linearly independent. Okay, so the first thing on the list is the definition, and the second thing on the list is to say that none of them is a linear combination of any of the others. Okay? And you can see that that would be really hard to check, because if there's like 10 of them, you'd have to say that this one's not a combination of any of those, this one's not a combination of any of those, and it would take ages to check. But it's much quicker to do the matrices, which is the next thing. So the next thing you would do is if you have a matrix with the vectors as columns, okay? So it's a matrix with the vectors as columns, because vectors are supposed to be columns anyway. It row reduces to give you a pivot in every column. Okay? So if there's a pivot, as in one of those leading ones, you don't have to go all the way to the reduced row echelon form. You only have to go to the stage where you can tell where the pivots are going to be. So if you can, with some row operations, tell where the pivots are going to be, and there's going to be one in every column, then they're linearly independent. Okay. There's a much longer list of things that tell you that things aren't. Linearly independent. Okay, so my list of things that tells you that they're not linearly independent is that it's from the definition. So first one is from the definition. You know, it's possible to write A1 V1 plus AK VK equals the zero vector without all the A's being zero, with at least one A not being zero. Okay, so that's when it's not linearly independent. I better put that in there. Okay, the next thing on the list is that one of them is a linear combination of any of the others. So any one vector is a linear combination of any others. Okay? I don't need one of them to be a linear combination of all of them, because I can just chuck zeros in for the others. Okay? So if any one vector is a linear combination of any of the others, even if it's just one of the others, then it will be linearly dependent. And the matrix with vectors as columns row reduces to get a column with no pivot in it. Yes?
Does that first rule include the zero vector?
I'm going to say that separately, but yes, it does. Row reduces to get a column with no pivot, so a free variable. But we don't actually care about the free variables themselves, because the free variable itself, putting in free variables, is a waste of time. It doesn't actually tell you anything useful. So you just want to find a column that doesn't have a pivot. Okay, you must put them in as columns for that rule to work. If you put them in as rows, then you'll be looking for something entirely different, and you don't learn about that until, well, they don't teach you in Maths 1B, but it is there technically. Okay, so these three will always work, okay? So these three, if you're not in that situation, it will have to be linearly independent, but there's two more rules. One of the vectors is a zero vector. So if you look at a list and one of them is a zero vector, it's automatically linearly dependent. Okay? And that works with all of these rules. It's possible to write that to come out to zero by just doing one of the zero vector. Or one of them is a linear combination of the others. Well, zero is a linear combination of everything, because it's just zero of that and zero of that and zero of that. And this matrix, if you've got a column of zeros, it's impossible to get a pivot in that column. And so you're going to get, so this fits with all of those. Okay, but just because zero isn't in the list doesn't mean it is linearly independent, okay? So that's why it's in a separate category. If it doesn't have zero, you have to use one of the other laws. And then the other one is if you have more vectors than the number of coordinates, then they'll be linearly dependent as well. Okay, so if you have more vectors than the number of coordinates that are in the vectors, then they'll be linearly dependent too. So if I'm in R3, where the vectors have 3 coordinates, and I have anything more than 3 vectors, then they're guaranteed to be dependent. It's a classic exam question to give you a list of vectors, you know, part A and there's a list, part B and there's a list, and say, are they linearly independent or not? And it should be possible for most of them to just look at it and go, that one's got the 0 vector, it's dependent. That one's got too many vectors, it's dependent. Look, that one, this is 2 times that, that's dependent. And be able to do it without having to actually do any matrices, except for maybe one of them. Okay, right. Why would we care if they're independent? Well, that's to do with subspaces. Okay, but it is something that you can say about vectors. And because it's so highly important to us that we can do linear combinations, we really want to know if we can make other vectors, some vectors out of other vectors using linear combinations, which is what this is all about. Cool. So I've been talking about this for about, 50, 45 minutes or so. And I still haven't got to subspaces, but now here I am. Okay, so subspaces are objects in their own right. The idea behind it is I can colour in a set of points in R3 or R2 or R7, and together those points make a subspace. Okay, so the subspace doesn't belong to any one of its points. All of those points together make the subspace. But it is an object in its own right. And so as an object in its own right, we can ask, what is it? We can ask, what can we say about it? We can ask, what can we do to it? And we can ask, what can we do with it? And you don't really have the last 2 answers, though you will be able to answer some of those in Maths 1B, because you'll do more subspace stuff there. But the first 2 we can get a really good handle on. Okay, and what is it has 3 subcategories of what isn't it, and what ways are there of representing this thing. Okay, so that's what you're learning in Maths 1A. You're actually learning about how to represent subspaces. So before I give you the definition, in fact I will give you the definition, and I'll write it down in a minute so that we can point it out, but you need to be able to look at something and know if it's a subspace or not, just by looking at it. And not use the definition, but just know, okay? Your lecturers expect you to be able to do that, because if they ask you an exam question that says, is this a subspace? You can just say whether it is or not. You do not have to prove it's a subspace. And it's a really good skill to know so that you can just know. And that's a good thing to do for anything, right? If you're a biologist, you don't want to have to actually look up the big dichotomous key to be able to tell if something is really an acacia tree. You need to be able to just look at it and go, oh, yes, yes, it is. Okay? So it's the same deal. Right. So there is a definition, and I will do the definition shortly. But before I do the definition, I'm going to give you a list of things that are and a list of things that aren't. Okay. Or am I? All right. In fact, I will write down the definition. But I'm not going to talk about it at length without doing the examples. So, to a mathematician, the definition is what the subspace is. Okay? So, if you are ever asked in an exam or by a mathematician, what is a subspace, then what you will respond is you will respond with the definition. You will not respond with a list of things that are and a list of things that aren't, even though that's what's in your head. You will respond with the definition, because that's what mathematicians want to hear when they ask, what is it? So the definition has 4 parts. And I know you think there's 3, but there's a secret 0th part. Okay? So the definition goes like this. Technically, a subspace belongs to something. It's not just a subspace raw, it's a subspace of something. So a subspace of Rn is a set of vectors which is in Rn. So this symbol here, it's different to the one I wrote before. The one I wrote before was this. And this is reserved for small object being inside big set, okay, a vector being in a set. This symbol is designed for a set being inside a bigger set. Okay, so this is the in for sets. Because this S is a set and so is this Rn. Whereas if I had just a vector like V underline, I would use the other in. Okay, so a subspace of Rn is a set of vectors, and that's the first rule. It's a set of vectors. Really important to remember that. It's a set. So all that stuff I said about sets applies to subspaces because they are sets. Okay. Where? And there are 3 rules. Rule number 1, you don't know which rule is which number you give to which rule is irrelevant. The point is that there are 3. So rule number 1, the 0 vector is in S. You don't technically need the 0 vector to be in there to be sure, you just need it to have a vector at all. Okay, it's not allowed to be the empty set which doesn't have anything in it at all. It has to have a vector. But if it doesn't have any vectors at all, it will have the 0 vector, and so you can check that, and then it's easier to put it in the rule. Rule number 2 is that if you do have a vector in the set, which you must because it has to have a vector, and k is a number in the real numbers, then kv, whatever that vector works out to be, that new vector has to still be in the set. Now you might know that as rule number 3. I put it as rule number 2 because it's easier to check than rule number 3. So if you're ever proving that things are subspaces or trying to prove that things aren't, it's much easier to do that rule first because it only has one vector in it. The rule number 3 is that if you have 2 vectors that are in the set, then the new vector you make by adding them together, that new vector as a point, it's in the set too. The real important thing to know about this is that these rules have to work for every possible vector that's there. Okay, every possible vector that's there and every possible scalar, that has to work for all of them. So if there is any of these rules are broken for any one vector, it's not a subspace. Same as saying, it's like saying, if I break the handle of a mug, it's still broken. It might be quite serviceable as a mug, but it's still broken. I only have to break one part of it for the whole thing to be broken. Okay, so it might look pretty good as a set, but it won't be a subspace even if just one vector breaks the rule, or any rule. Okay, that's the definition. I'm not going to talk about that until I've done lots of examples of a list of things that are and things that aren't. So, things that are. So in future, if you're ever faced with a definition of a kind of object, you should make for yourself a list of things that are and a list of things that aren't. And every time in the lectures it comes up as an example of something that turned out to be or something that turned out not to be, add it to the list so that you can get a picture of what it's like. Because human beings do not work by definitions. Okay, human beings learn what things are by seeing lots of things that aren't and lots of things that aren't, and then you can tell. So as a child, you learned what dogs were by seeing dogs and seeing things that aren't dogs. Okay, and so it's the same thing with maths. You just have to do it yourself. Okay, so things that are. Okay, the most basic thing that is just the origin all by itself as a set. No, look at this set. It's not the origin, it's a set with the origin in it. This is the listing type of making a set. I list all the things that are in the set, and the only thing that's there is the origin. It's a subspace all by itself. A line through the origin, a plane through the origin. They're your basic subspaces. Okay, and the nice thing about those 3 things is that you can picture them as pictures. Okay, the set that contains the origin is just a dot, and a line through the origin we can draw that, and a plane through the origin we can draw that too. Do remember they have to go on forever, Even though when we draw planes, we draw them as rectangles, they have to go on forever. And also, you could take the entire of Rn, and it's a sort of a technicality that it's a subspace too. So you are allowed to go, oh look, I've just got everything, yep.
Do you draw some sets from the line through origin and plane through origin?
I will, I'll draw it as pictures too.
Just write them.
Sorry, what's that?
Could you just write like an example?
Oh, well, as in what it looks like in set notation? Yes, I'm getting to that. So the question was, could you please write some sets in set notation and what they look like? I will do that, okay? Okay, so this is pictures, this one, okay? We're thinking about it as a picture here of things that are. Over this side, I'm going to put some things that aren't. Okay. So some things that aren't. Okay, as it turns out, all subspaces will be roughly this shape, except possibly instead of a plane, it might be a three-dimensional thing in four-dimensional space, okay? So if we just look at those as just pictures, the line through the origin has to go through the origin, but it's continuous, it doesn't have any gaps in it, and it also goes on forever. So anything that doesn't go on forever is not a subspace, and anything that has holes in it is not a subspace. Okay, so if you can imagine it as a set, then it won't be a subspace if it's got holes in it. So things with holes. So for example, if I had everything except this circle, except the inside of that circle, that would not be a subspace because it's got a big hole in the middle. And not just because it doesn't contain the origin. Even if I put the origin back, it would still not be a subspace because it has a hole. And the reason that works is because if I pick a point that's in it and divide it by like 3, I will end up here. And that's in the hole, and therefore scalar multiplying produces things that aren't in the set anymore, and so it's not a subspace. You know, if I just had a line that just went from here to here, that wouldn't be a subspace either, because I could get this point and multiply it by 2 and end up out of the thing, out of the set. So that's not a subspace either. So it's not allowed to have gaps at the outside, it's not allowed to have gaps on the inside, it's not allowed to have gaps anywhere. Another example, a single line through the origin, if it went on forever, would certainly be a subspace. But if I had 2 lines through the origin, that thing together as the letter X is not a subspace because it has a gap. There's big gaps here. Okay? Any point I can certainly multiply it by something and end up still in the subspace, but if I take one here and add them together, I will get that one there and it's not in the set anymore. Okay? So this set isn't a subspace because it's got a gap. If you're in an exam and they give you a reason, you're not allowed to say it has a gap. You are allowed to, though, draw the picture and find some points and say, well, if I pick the point 1, 1 and the point minus 1, 1 and add them together, I get the point 0, 2, which isn't in the set. Okay, so it helps you find examples. And also, continuing my list of things that aren't, lines that go through the origin are subspaces. Any line that doesn't go through the origin is not a subspace. So a line not through the origin, a plane not through the origin. Obviously, if it doesn't go through the origin, it's not a subspace. But I want to point out that it breaks a line not through the origin like this. Breaks all 3 of those rules. It doesn't have the 0 vector in it. If I pick a point in it and treat it as an arrow and say multiply it by a half, I will get a point that's not in the set. And if I pick a point somewhere and another point somewhere and add them together, I will get a point that's not in the set. So no line that goes, a line through that's not through the origin is in a way the worst possible non-subspace. Okay? So even though a line through the origin is a subspace, lines that don't go through the origin are the worst kind of not subspace. Okay, so that's pictures. If you've got pictures in your head and they are of this type, you can tell from the picture whether it's a subspace or not. The next stage is to know just from how it's written, is it a subspace, which is what you're getting at. So, I should put a dot there. Okay, right. So, there are two main ways to make a set, right? So, well, there's four, and I will list all of them so that you can see what's going on. The two most important ones are the middle ones, which are making by equation and making by construction. So if I'm going to construct a set, these are just examples. So for your reference, this is a line through the origin. It will look like that. And this is a plane through the origin. And that will look like that. I know it's a line because I can whack in a 0, 0, 0 plus t of whatever. So it goes through 0, 0, 0 and it goes in this direction. Okay. Those two are examples of subspaces. Anything that's written that way must be a subspace. But there is a caveat there. You have to be able to use all of the real numbers. If there is a restriction and there is any one number you're not allowed to use, then it's not a subspace. So these are all subspaces. And it doesn't matter if you repeat the vector multiple times. It doesn't matter if the vectors are linearly independent. It doesn't matter at all. As long as it's something times vector plus some linear combinations, then it's a subspace. Okay. And this is shorthand for span. Okay, this is the span of 1, 2, 3. That's what this is. And this here is the span of 1, 2, 3 and 4, 0, 1. This word span is shorthand for this. Okay, it's just a quick way of writing what's here. That's all span means. Okay, so I will talk about span properly in just a minute. So span is a set, okay, and therefore being a set it must have a rule for being in or out. And the rule for being in or out is that you are in if you're a combination of those things and if you are out if you're not. So it is a theorem in your lecture notes that you are allowed to state that anything that is a span is a subspace. So the span of any vectors is always a subspace. If you are able to rewrite it so that it is a span, then it's definitely a subspace. Okay, so if you are able to look...
What do you mean by rewrite it?
What do I mean by rewrite it? Let me just... I'll do an example in a second. If I don't do it by the time I get to the end of this list, remind me, okay? Okay. I'll do an example in a second. Okay. So, yep. And the next thing on the list would be ones that are made by... Oh no, before I do that, I should do some things that aren't in the span sort of category. So if I had this, you know, R1, 2, 3 plus 1, 1, 1, such that R is in R, that would not be a subspace. And the reason is, it's surely a linear combination of stuff, but I'm only allowed to use a number 1 for this one. So I'm completely restricted. I'm not allowed to use all possible combinations of these things. I'm only allowed to use one. This combination has to be a 1, and therefore it's not a subspace. And the other reason is that this is a line that doesn't go through the origin. There's a special case of this, which I'll do in my example, where if this happens to be a multiple of that, then it comes out to be a subspace anyway. But you've just got to be careful in that, okay? So this is not all possible combinations. And then the next version of that would be something like R of 1, 2 plus S of 1, 1, such that R and S are in Z. Okay, so I'm only allowed to use integers for the R and the S. Therefore, I can't produce all the possible combinations. I'm not allowed to do a half of R, for example, like a half of 1, 2. So therefore, it's not a subspace, because I haven't used all the combinations. Okay? Okay, so it has to be, span means you have to use all the combinations, and if there's any one combination that's missing, it's not a subspace. And that combination has to be allowed to be any real number at all. Even if I was allowed to use all the fractions, but I couldn't use pi, it still wouldn't be a subspace. I have to use all the real numbers. Okay. The next rule is how to make it using equations. So if I had some equations that were defining my subspace, I have, you know, vectors and they have to satisfy equations. If those equations are linear and they are homogeneous, so linear equal to 0, it doesn't matter how many equations there are, if they are linear and equal to 0, then it must be a subspace. And that is also something in your notes. Okay, so if it's, you know, vectors such that linear equations that are equal to 0, like homogeneous linear equations, then this must be a subspace, okay? The other way of writing it is that solutions to Ax equals 0, where A is a matrix, that's always a subspace too. And that's because Ax equals 0 is really just another way of writing linear equations. So these are in the same category. Okay? Anything that can be rewritten as a matrix equation or that has linear equations equal to 0 must be a subspace. So you can, just by staring at it, so just as some proper examples, you know, x, y, z in R3 such that x plus y equals 0, that's a subspace. And x, y, z, so maybe just x, y, xy in R2 such that x plus y equals 0 and z equals 0, that's a subspace. That in fact will just be the origin, but you know, that's fine. It doesn't matter how many equations you've got, it doesn't matter if they only include one of the variables, it doesn't matter if all the variables are there or not, as long as it's linear. I can have 2x plus y, that's fine as well, it doesn't matter if they're negative. As long as it's a linear equation, as many linear equations as you like, as long as they're all equal to 0, it will be a subspace. Okay, and the other one would be something like the set of the set of x, y in R2 such that one okay, that's another one. It's just written with matrices instead of with linear equations, because I can expand that out to make linear equations. Okay? All of those must be subspaces. And you can just look at them and go, linear equations equal to 0, subspace. Because you're allowed to say that. Okay. But on that note, we should talk about what it would look like if it wasn't a subspace. x squared plus y equals 0. That's not a subspace because the equation is not linear. There is a special exception to that, where if they're both squared and they're both positive, then it will be a subspace anyway. So that's sort of your double bluff, and I'll put that in the other category. That's not linear equation, okay? So it's an equation, but it's not linear. Another non-linear equation that's worth knowing about is something like xy. Okay, if the x is times by the y, that's not linear either, so it won't be a subspace. And even if it is linear, if it's not equal to 0, then it won't be a subspace. Because what it will represent is a line or a plane or something that doesn't go through the origin. So remember, I can always check to see if something is in this subspace by subbing it in. 0 plus 3 times 0 is not 1, and so therefore 0 is not in there, so it's not a subspace. But these ones do have 0 in them, but they're still not subspaces. Okay, so not equal to 0. So they're not. Okay, so there is one special case. That one there, special case, that is a subspace, because the only vector that satisfies that is the origin, and therefore that's all there is, and therefore it's a subspace, because the origin all by itself is subspace. Because the only solution is xy equals 0, 0. Okay? Right. That's my list of things that are and things that aren't. Okay, so it would be useful to just do a couple of examples of deciding. So R plus S, T minus 3S, such that RST is in R. So let's think about this. This is a set, so it can be a subspace because it's a set. The set itself is in R3 because it's made of coordinates, vectors which have 3 coordinates. So technically it's in R3. That's an important thing to note. So we do have a set that's in R something, and so therefore it can be a subspace. And this set has been made by construction. And so my rule for telling if something's in the set is that if it's possible to write the coordinates in this way. What I'm going to do is I'm going to rewrite this so that I can tell that it's a span. So I'm going to separate this into a vector with the r's, a vector with the s's, and a vector with the t's. I've got one r in the first coordinate, one r in the second coordinate, and no r's in the third coordinate. With my s's, I've got no s's in the first coordinate, one s in the second coordinate, and minus 3 s's in the third coordinate. I've got no t's in the first coordinate, no t's in the second coordinate, and one t in the third coordinate. And now what I've managed to do is say that it's actually r of a vector plus s of a vector plus t of a vector, where the r and s and the t can be anything I want. I'm allowed to choose all possible r, s's and t's in the real numbers. That means it's a span, because that's what span is. That's what I mean by rewriting as a span. So you can add that to your list if you want to, of recognizing if it's made by telling you what each of the coordinates is separately, and each of those coordinates is a linear thing, then it will be a subspace. So you'll see how this here is linear. These are all linear combinations of S, T, and R. If that's true, if all of the coordinates of the points that you make are linear combinations, and you're allowed to use all the possible real numbers, then it will be a subspace too, because it's a span. Okay. So those are all the things that are subspaces. which means that I can make decisions by just looking at stuff and go, yep, linear equations must be a subspace. Okay, yep, oh, it's a span, must be a subspace. Oh, it looks like a span, but I'm not allowed to use all the combinations, not a subspace. Okay, those are the sorts of things you're allowed to do. But I should say, just as an example, if you get one that you're sure isn't a subspace, oops, xy is such that x times x minus y is 0, that must be on this. I know it's on my screen. Okay, you can't even see that. It's baked in. Okay, so if you see something like that, that's not linear because the x is going to be times by the x and I'm going to get an x squared, so it's not a subspace. I know that it's not going to be a subspace because that's not a linear equation. Okay, but you saying it's not a linear equation, therefore it's not a subspace, is not good enough because there are things where it's not linear that are subspaces because we've seen one, this one here. That's not linear, but it's still a subspace. And so my instinct tells me that it's not a subspace, but I need a really good reason why not. Okay? And the only really good reason in an exam for why I think something is not a subspace is to find some vectors that break the rules. Okay, so I need to think of some vectors that are in it and break the rules. Now, things, there are nonlinear equations often break the scalar multiplication rule, but that only counts if all the powers are different. So you'll notice with this one, if I expand this out, I'll get an x squared and an xy. An xy, because there's two things multiplied together, still counts as a square. So this one's actually going to satisfy the scalar multiplication rule. So I know the addition rule is the one that's going to have to break. But I can also attempt to draw this set. This will be, well, it will be either x is 0, which would be the y-axis, or x minus y is 0, which would be the line y equals x. So that's what this actually is. So this set, to solve this equation, either x is 0, which would be the y-axis, or x minus y is 0, which would be this line here. So this is one of those two-line situations. So as long as I pick something on one line and something on the other and add them, then that will break the rule. So what if I pick the point 0, 1 is in, let's call it S, is in S, since 0 times 0 minus 1 is 0. And I need another point, maybe 1, 1. 1, 1 is in S, since 1 times 1 minus 1 is 0, but 0, 1 plus 1, 1 is 1, 2, which is not in S, since x times x minus y is minus 1, which is not 0. That's an acceptable rule for things not being subspaces. You are allowed to use the one where if it is linear but it's not homogeneous, you are allowed to say it's linear but not equal to 0, so therefore not subspace. That's okay. But anything else you're, well actually that just means if you sub in 0 it doesn't work. Anything else you have to break one of the rules. So what happens is if your equation has several pieces that are multiplied together, you want to find a point that satisfies this one but not that one, and a point that satisfies this one but not that one, and when you add them it won't work. So that's the hardest kind. The easiest kind are the ones that are like this. So showing that things aren't subspaces. That one there, that's, if I rearrange that, that's y equals minus x squared, so I can imagine what that looks like. Y equals minus x squared, which is totally not a subspace because subspaces have to be straight lines. And it's easiest to break this with scalar multiplication because I just think of something that works, like 1, 1, which is 1 and minus 1. And if I multiply that by 2, I'll end up over here. So 1, 1 is in S since, no, 1 minus 1, sorry. Since 1 squared plus minus 1 is 0, but 2 minus 2 is not in S since 2 squared plus minus 2 is 2, which is not 0. And so scalar multiplication doesn't work, so therefore it's not a subspace. Therefore S not a subspace. Okay, there you go. So scalar multiplication normally breaks, even if you don't draw a picture of it, even if you can't picture what it looks like, if it's a nonlinear equation and they're not all to the same power, then scalar multiplication is what's going to break. The final classic example is x, y, z, such that x, y, z is in z. That only has integer coordinates, and so you could say that 1, 1, 1 is in S. So it would be a span, because that would be x of 1, 0, 0, y of 0, 1, 0, and z of 0, 0, 1. That's a perfectly good span, except I'm not allowed to use all the combinations, and so it's not a subspace. And 1, 1, 1 is in S, since 1 and 1 and 1 are all in Z. But a half of 1, 1, 1 is not in S, since its coordinates aren't integers. So S is not a subspace. So as you can see, it's always much easier to break the multiplication, to try breaking that first. I think I just turned the heater on. Because it must be something to do with the outdoor temperature. Okay. So I should want to point something out. This set will actually satisfy the addition rule, but not the scalar multiplication rule. And this set will satisfy the scalar multiplication rule, but not the addition rule. So it is possible to have any combination of those three rules being true or false, but only when all three of them are true is it a subspace. Except the 0. That ties in too closely to the scalar multiplication. Okay. Awesome. So where are we up to? We've talked about vectors. We've talked about what things are and what things aren't subspaces, so that we can just stare at things and know. I guess I should talk about how to prove that something's a subspace. All right. But maybe before I do that, because that's actually the hardest part of this, I'll skip back to proving it later. So if you want it in a decent order, then you can leave space for it. It'll take about 2 pages, let's say, of my pages. I write pretty big. And I'll do basis first, because proving that things are subspaces is a different story entirely. Okay. So, basis. All right, so the objects we've seen so far today are vectors, sets, and subspaces. A basis does not count as an object in its own right. A basis is just information about a subspace. Okay, it's not its own thing. Okay, in the same way that your nose is not an independent living creature, it's a part of you, it's the same thing. A basis is not an independent object, it doesn't exist separately from its subspace, it's just information about a subspace. Okay, so that's the most important thing to remember. Okay, so when a lot of students talk to me, they say, oh, is this a basis? And they're pointing to a subspace. Okay? Or they'll point to a subspace and say, oh, is this a basis? And I'll say, well, no, because a basis is just information about a subspace. Okay? So it's information about a subspace. So to have a basis, you have to have a subspace that it's a basis of. Okay? Right. And the whole idea of a basis, this is the idea is to write your subspace as a span. That's what it is. The whole idea is to write your base subspace as a span. It might currently be a span already, or it might currently be written as equations. Your aim is to convert it into a span in such a way that you use the minimal amount of vectors to span it. Okay? So in brackets, most efficiently. But the key point is, the most efficiently we'll deal with later, the key point is we want to write it as the span of something. Okay? And the something that you span is the basis. Okay? So the idea is that if we have i.e. S is a subspace, we write S equals the span of some vectors. Those vectors together, these vectors here that are inside the span, that's a really, really wonky brace. These vectors here that are inside the span, they are the basis. That's what a basis is for. It's just information that goes in this spot so that we can create our subspace from a span. Pictorially, it's some starting directions. Okay, so I know that all subspaces start at the origin. If I pick some directions to go, I'll be able to create the rest of my subspace from just those directions. So my aim is to create all the rest of the subspace by doing combinations of just a few vectors. But this is what it's all about. It's about writing things as a span. So if your subspace is not currently a span, then there is no basis for it yet, because you need to rewrite it as a span first. Okay. That's the idea. And that's something to hold on to. Okay? If you can write it as a span, then you'll be able to find the basis. Okay. Just geometrically, the point of a basis is to mark out coordinate axes inside your subspace. Okay, so in 3 dimensions, well, in 2 dimensions, so they're coordinate axes. So here I am in R2. I could use, if I had made a basis for R2, what I could do is I could write R2 as the span of a couple of vectors. So I could choose this point here and this point here, which would be 1, 0 and 0, 1. And what I can do is I can think of them as arrows so that I can add them and scale and multiply. And I can go, well, if I do 2 of this, I'll be able to make the point 2, 0, and I can mark the point 2 on my axis. And I can mark the point 3 on my axis by doing 3 of them, and minus 1 I could mark that point. And I could mark all the points on my axes in both directions. And then any point, and I can always also go halfway, because I can have, this would be a half, because it would be 1.5 of those. And then any point here I could write as some of this and some of this, and figure out what its coordinates are in terms of the 0, 1 and the 1, 0. But I could also, I could write this as some of this one and some of this one. Okay? But what I could also do is I could choose some other basis. So maybe I'll pick, this point and that point there, and as arrows they're like this. Okay? And I could mark out new coordinate axes based on those. So I could mark out an axis here and an axis here, and then I could have, this would be 1 and then be 2 here, because that's 2 of my basis vector, and 3 and 4, and this would be 1 here and 2 of that and 3 of that, and this would be minus 1 here. And they're not marked in the same size, but it doesn't matter. And that means at any point, if I had a random point in space, in maybe purple, this point here, for example, I could try and figure out what it is in terms of my basis. Well, I'll go, come back to this axis, parallel to that one, and this one parallel to the other, So it looks like I can go like 1.5 of my first basis vector and 1.8 of my second basis vector. So I can say that this is 1.5 of my first basis vector and 1.8 of my second basis vector. Okay? So I'm marking out new coordinate axes. In Maths 1B, you will learn how to find coordinate axes that are at right angles to each other and whose basis vectors have length 1 so that they really are coordinate axes. Okay? Because part of the purpose of all of this is that you might have some random shape and some formula, some random shape, and you want to find a nice way of describing it. If you happen to see in R2 something like that, which is an oval, it might be much easier to write its formula if I drew my axes here. Okay? So what I can actually do is I can create a coordinate system for R2 starting at this point and using these directions as my basis. Now at the moment you're only starting at the origin and you're not concerned about the right angles yet, and that comes in Maths 1B. But that's pictorially what the purpose is. So I could, if I wanted to, rewrite, this point has its own coordinates, it lines up with an x and a y here, but I can rewrite it in coordinates based on the v1 and the v2. And that's what it means to write something as a combination of the basis. And you'll notice that because I was in R2, I needed 2 coordinate axes. 1 coordinate axis wouldn't be enough to find that point. Okay, so I need at least 1. And 3 coordinate axes would be overkill because there'd be more than one way to get to that spot. Because if I had a third one, say, going up here, I could do this and that, but I could just do this and a bit of the third one, and there'd be multiple ways of achieving that point. I want it so that there's only exactly one way to get to that point using my basis. Okay? So that's what I mean by most efficiently. And you arrange for that to happen by making sure that your vectors are independent of each other. And that's why we care about linear independence, because it means that if we start with some vectors that are linearly independent, then the thing that we span from them will only be, every point in there will only be spanned in exactly one way. Where's my paper? Okay, so that's the idea of a basis. The definition is this. So, because a basis is information about a subspace, you have to start with a subspace. Okay, so given a subspace S, traditionally your lecturer writes it as W, and I normally do too, but today I'm using S because that's just what happened. So given a subspace S, it does make sense, it starts with S, subspace, a word. So given a subspace S, a basis for S is a set of vectors, that's sometimes called a list of vectors, but it doesn't matter. Now, you know how it's a set, that means it must be a collection of vectors with a rule for being in or out. It's always a list set. It's rule number 1 for making sets, where you just list the things that are in it. Okay, so it's actually a list. You are allowed to use the word list if you like, if you want, just to remind you. So it's a list of vectors which, 1, span S, that's not span, it's stas, which span S, which means that S is the span of the vectors, and 2, are linearly independent. So this one guarantees that we've written S as a span, which means that we'll be able to find all the points in S using my vectors. And part 2, with the linear independent, guarantees that you're not going to be able to do it any more than one way. You'll be able to find every vector in S in exactly one way using your vectors, using your basis. So that's the definition of a basis. Okay? You can grammatically rearrange that sentence if you're asked for the definition. You can say a basis for the subspace S is, if you want. And you can actually list what the vectors are called, V1 up to VR or something if you want to. But that's just grammar, and this will be a perfectly good definition. Okay. Right. However, there is a secret zeroth rule. Just like with subspaces, they have to be in S. That's rule 0. If they're not in S, they can't span S. They'll span something, it just won't be S. Okay? Right. So if you are asked to find if a set of vectors is a basis for something, you should first check if they're actually part of the something they're supposed to be a basis for. Okay, so that's the definition. Just let me have a look. I did prepare a little. Okay. Right, so before I get on to actually finding a basis, one of the things that a basis allows us to do is have a really consistent definition to what we mean by dimension of an object. So we're pretty sure that a line is a one-dimensional object and a plane is a two-dimensional object. So we want to know when we do a subspace, it's some sort of object, we colour in all the points and we have an object in its own right. What dimension is it? Because is it a line, is it a plane, what is it? So we need to know what the dimension is. And our definition of dimension is how many vectors there are in the subspace, in the basis. Okay? So there's, this is the definition of dimension. Which I call rule number 3. Number of vectors in the basis is the dimension of S. And that's a consistent definition because if you do have a basis, they will always have to, they will all have to have the same number of vectors. And it is worth pointing out that any one subspace has infinitely many choices for its vectors, for its basis. Okay? So just like in R2 I was able to use my standard coordinate axes, I can put my coordinate axes wherever the hell I want and they will all tell me bases. And so there's basis in whatever direction you like. It means that people marking your exam have to be clever enough to be able to tell when you give them a basis that they weren't expecting, and they can tell, so don't worry about getting a different answer to them. Okay? As long as it really is a basis, then you'll be correct. So it's really important when you look at exam solutions, if they have a different answer to you when you're expected to find a basis, that's okay, because yours might still be a basis. Okay? So, your lecturer, because I told him to, told you already that any two of these rules here makes it a basis. And that's because he asked me, what should I tell them? And I said, you should tell them that. And he listened and I was so excited. So he told you already that, but I need to say it now just in case next semester, when next semester's students are watching this, they need to know. Any two of 1, 2 and 3 make it a basis. Oh, as long as you have rule number 0, that they're actually in S. Okay? So if you have the right number of vectors and they're linearly independent, then it will be a basis. They'll span automatically. If you have the right number of vectors and they span, then it'll be linearly independent automatically and there'll be a basis. And if you don't already know how many vectors you ought to have, then you've got no recourse but to do the first 2 rules. Okay? But if you already know the dimension, then you can find a basis by a bit more creative means. So I'm going to give you some examples of finding bases. Okay, now let's go back to thinking about my sets, right? So my subspace is a set, and my subspace can be written in multiple ways because sets can. And there are 2 main ways to write a subspace. There is the way where you construct all the vectors that are in the subspace, the construction method. That was rule number 2, and I did it before. And we need to know how to make a basis when we see a subspace mentioned in that way. And there's the equation method, and we need to know how to make a basis when the subspace is mentioned that way. And the method is different. Okay? So because The point is to write it as a span, and if it's already in construction mode, it's already a span. Okay? So there's actually 3. So if it's not, so just a second. Here's my advice. To find a basis, first rewrite as span. Okay? Because that's what a basis is for. So that method that I had before of rewriting something as a span, if that's the situation you're in, and you can look at it and go, oh, I could rewrite that as a span by just doing some algebra, some basic algebra, then do that first. Write it as a span first. Okay? And if it's already a span, awesome. Okay? So I'm going to start with one that's already a span. I have the span of those 3. So before we get any further, we should actually have a quick look at this and understand what's going on. If I span 3 vectors, then I know that if that the point of a basis is to write as a span, and then what you have in here is the basis as long as they're independent. So I know that if they're independent, this is the basis already. And if they're independent, and that was the basis, because there's 3 of them, it would be dimension 3. So that's great. Okay, so if that is the basis, it's the whole of 3-dimensional space, because there's only 3 dimensions to go around in 3-dimensional space. Okay, which seems pointless, but it might be true. Okay, all right. So, for example, if this was an exam question and they said S is this, what is S? You know, well, it's that. But if that basis is a basis, then what S is R3. Because it's all of R3. All right. However, I have specifically set this up so that it's not. We look at it and we know. Well, we need to know if that is linearly independent, because I've already got the first rule of spanning. And to know if they're linearly independent, I could chuck them as columns in a matrix. That would always work to tell me if they're independent. But I could also just have a quick squeeze to see if one of them is a linear combination of the others. Can anyone see it? Yep.
If you add the first 2, it's the third one.
So they're not independent because that one's a combination of those 2. And so I can remove that one because it's a combination of the other 2. So that's one way of doing it. So I could go, the first method. 1, 2, 5 is 1, 1, 2 plus 0, 1, 3. And so I have to remove the one that's the result, which is this one. So linear combination of the others. So S is in fact equal to just the span of the first 2. And now they are independent because they're not multiples of each other, and so therefore that's it.
And is that an appropriate way of writing it out?
Mm-hmm. And so therefore I would actually say my final step would be therefore 1, 1, 2, 0, 1, 3 is a basis. And that would be a perfectly acceptable solution in an exam. For S, technically. You actually have to say what it's a basis for, because technically it should be understood from context. But in a completely technical sense, if you take 2 independent vectors and then they're a basis for something, it just might not be a basis for the one you were looking for. So you should explicitly point out that they're a basis for S. Those 3 vectors that we started with weren't a basis for anything because they weren't independent. Okay. All right. My second method would be, what if I couldn't tell to start with whether they are independent or not just by looking at them? And so then what I would do is I would find whether they're independent. So find if vectors linearly independent. And so I'll put them as columns. And row reduce just that and see what happens. And row 3 is row 3 minus 2 of row 1. It would be okay for you to use a calculator if you wanted to in an exam, unless they explicitly told you to use row operations, obviously. Oh, and look at that. It's almost as if I set it up that way. And so now, that actually is reduced rational in form, but it wouldn't matter even if it wasn't, because I can tell that there's a pivot here, there's a pivot here. Even if they weren't ones, but there was some other non-zero number, I could tell that they will be pivots eventually, so I can stop. I don't have to go all the way to the reduced row echelon form. And so I have, but there's no pivot in the third column, no pivot in the third column, so they're dependent. But I also know that if I started with the first two vectors, then they would have row reduced to be independent, because there's a pivot in every column if I just use the first two. Okay? So basically what you should do is when you get to the end of that, you should find the pivots and then go back to the original columns that the pivots came from, and they are your basis. So choose columns with pivots. So 1, 1, 2, 0, 1, 3 is a basis for S. And that would be a different and perfectly acceptable. And note that they don't have to be next to each other, you just have to find the pivots, because sometimes when you do row operations you end up with a gap where there's no pivot somewhere in the middle. That's okay, as long as you choose the ones that the pivots came from. In Maths 1B, you will find a different method of doing this, where you put the vectors as rows. You'll be looking for something different at the end. Okay? But don't put them as rows, because it won't work this way if you do it as rows. Okay. So that's if it's already a span. If it's not already a span and is instead a set of equations. So I do have an example like that already here. Yeah, I'll put W there. I know that frustrates people for them not to be in alphabetical order, but for most people the first coordinate should be X. Okay, so this is one that's written as equations. Do note that sometimes they leave out this bit and they just say X plus Z equals 2Z minus W equals 0. That's really two equations. It's this one equals 0 and that one equals 0, so you need to convert. Okay, don't treat this as one of the equations. You could, and that would work, but it would be simpler to just say, well, since they're both equal to 0, this one's equal to 0 and that one's equal to 0. So what we actually have to do, this is currently not written as a span. This is currently written as an equation. Okay, I have to solve some equations, and therefore I need to rewrite this as a span. And a span fundamentally is a description of what all of the points in this subspace are. So I need to find all of the points in this subspace. Okay? Which means I need to find all of the points that satisfy those equations. So that's the reasoning behind this. I need to find all points in we call it S. In S. So we will solve X plus Z equals 0 and 2Z minus W equals 0. We will solve those. And that's how you always start. And this is how to convert something that's equations into something that's span. So I've got X, Y, Z and W. my first equation is 1x and no y's and 1z and no w's equals 0. My second equation is no x's and no y's and 2 z's and minus 1 w's is 0. And then I solve them. Note that in both of these settings I'm using row operations. Well, I don't have to in the first one, but I could. In both of these settings I can use row operations, but when I've finished my row operations I'll be looking for different things. Okay? In the first one I was looking for the pivots themselves, and I was going back to the original matrix to get the columns that they came from. In this one I won't be looking for the pivots themselves. Okay, so I can, if I want, technically put pivots wherever I want, as long as there's together the pivots make an identity, the pivot columns make an identity matrix. So traditionally what you'd do is you'd put one there and then you'd put one here, which you could do if you wanted. So I could divide that one by 2. But I could just as easily have a pivot column here and another pivot column here, just like we did when we did slack variables. So I'm actually going to do row 2 is minus row 2. And notice that here is where my pivot columns are, because together they make an identity matrix. Or at least they are as much of the identity I can make, and I managed to make the whole thing. And the other 2 columns are free variables. So I have that y and z are free. So what we'll do is we'll let y be s and z be t. And therefore from this one, x plus z is 0. So therefore x is minus z, and so therefore x is minus t. And from this second, so from the first row, and from the second row, minus 2z plus w is 0, and so therefore w is 2z, which is 2t. I need to point out, there's a column of zeros here. That means that that variable is free. Do not ignore it. It does not mean that that variable is 0. It means that we know nothing about y, so it can be whatever we want. Okay, so I can now get that x, y, z, and w. X is equal to minus t, y is equal to s, z is equal to t, and w is 2t. The variables I have are t and s, so I can have a whole vector for the t's and a whole vector for the s's. In the first spot I have minus 1t, there's no t's there, there's 1t there, and there's 2t's there. And then over here with the s's, there's no s's in the first spot, there's 1s there, there's no s's there, and there's no s's there. And so that is my solution. Okay? You'll find that if you do get a column of zeros, then the free variable that goes with it will have an identity matrix column as its vector. So, yeah. Now, right. So what we've done is we've found all the vectors in S. S is now, we don't have to write this step, but I will write it anyway. So S is in fact the span. Well. In fact, I'll write this in, but we don't have to write either of these steps if we don't want. S is the set of t minus 1, 0, 1, 2. I'm being a bit sloppy switching from rows to columns and columns to rows, but my original thing had it written as rows, so I should do that with my final answer. Okay? It's just the reason I have to write them as columns in this calculation is because to put a vector next to a matrix, it has to be a column. So plus s of 0, 1, 0, 0, such that t and s are in R. That's what I've got. That's what this says. This says that my s has been converted into this, and this is actually the span of minus 1, 0, 1, 2, and 0, 1, 0, 0. Because it's all the combinations of those two things. Anytime I see t of something plus s of something and the t and s are allowed to be all real numbers, that's what span means. And so I just need to check if they're independent, and in fact I don't have to because this process always makes independent vectors. So I don't actually have to check. but I can tell because this is not a multiple of that. Okay, so therefore, minus 1, 0, 1, 2, and 0, 1, 0, 0 is a basis for S. Okay, you don't have to put those two lines in. You can go straight to this if you want, which will cut down time in the exam, but it's just good to know that that's what's really going on here. Okay, so the two vectors that you get here are the basis. So my final example is a little bit different to these. Okay, so they're the classic ways of finding bases. My final example is a little different, and it goes like this. All right, that one. I know it's a subspace because it's got a linear equation. In fact, because it's only got one linear equation, I know it's going to be a plane because one linear equation always makes a plane in 3D. If it was in 2D, one linear equation would make a line. Okay, so I know this is a plane. And because I know it's a plane, I can use the fact that a plane has dimension 2 to help me find a basis. Okay, so there's two approaches to this I'm going to show you. The first approach is not the one I just mentioned. So approach number 1. So approach number 1 would be to solve that equation. The same as the other question. It's currently written as an equation. I need to rewrite it as a span because that's how to find a basis. Okay, so I'll do exactly what I did in the last problem, which was, where did is there? No. Just a second, I've lost a page. There. Oh, right, okay, I've got it. So we need to find all the points in S. Find all points in S, which means we solve the equation. Well, there are in fact two ways to solve this equation. One is to go, well, x minus z equals 0, so therefore x equals z, and therefore my points x, y, z are actually z, y, and z, because x equals z. And so therefore this is z lots of 1, 0, 1 plus y lots of 0, 1, 0. The same trick I normally do with free variables. I've got a z and it's got 1 here and none here and 1 here. I've got a y, there's none here and 1 here and none here. And so therefore S is the span of 1, 0, 1 and 0, 1, 0. And therefore 1, 0, 1 and 0, 1, 0 are, or technically is, a basis for S. That's one way. That's a particularly nice one. If you had a more complicated equation, you'd just rearrange it so that one of them was equal to the others and you'd sub that in. Approach 2 is similar. You can pick whichever approach you like right in the exam, and I'm trying to point out that if you like one better than the others, then go for it. So we're going to solve the equation. So we have x minus z equals 0. So I could, if I wanted to, do my x, y, z, and I've got 1x and no y's and minus 1 z's equals 0, and do it as a matrix. But this matrix only has one row. So I don't have to do any row operations because I have a pivot just here, and then the other two variables are free. So I could do that if I wanted. So I could go y and z are free. So we'll let y be s and z be t, and therefore x equals t, and we'll get that x, y, z is t, s, t, which is t times 1, 0, 1 plus s times 0, 1, 0, and so therefore 1, 0, 1 and 0, 1, 0 is a basis for S. Okay, that's method number 2, which is not really essentially different from method number 1, but I just thought I should point out that that's how to solve a linear equations if there's only one row. And approach 3 would be this approach. S is a plane, since it is one linear equation in R3. Okay? Therefore, S has dimension 2. And I know that any two out of those 3 rules makes something a basis. So, well, I have to have the points being in S. So if I get 2 points in S and they're independent, they will have to be a basis, because I'll have 2 out of those 3 rules. So if I can just find some vectors that are in S, I'll be good. So this is cutting down on the work because I don't have to find all the vectors in S, I only have to find some vectors in S. So what I can do in my head is I can look back at my definition of S, which is there, and go, let's think of some vectors. So have a look at this. We need x minus z to be 0. So we could have x and z to be 1 and 1, right? And it doesn't tell me anything about y, so I can do whatever I want. So I've got that 1, 0, 1 is in S since 1 minus 1 is 0. So I just happen to think of that one off the top of my head. And 1, 1, 1 will be in S too, since 1 minus 1 is 0. Because I can make y to be whatever I want. And those 2 vectors are independent. They're independent, and there's 2 of them, and the dimension is 2. And the number of vectors equals the dimension of S. So therefore, 1, 0, 1 and 1, 1, 1 is a basis for S. So that's another approach to finding bases. Okay? Any of them would be okay. Obviously, this one will only apply in certain situations where you happen to notice stuff. Okay, so usually the other approaches are safer, but it's good to know that you can do this if you want. Okay. All right. Well, that's probably everything I have to say about basis, except possibly doing some proofs with that. I've already been going for 2 hours now, 2 and a bit. If you want me to, I will continue and talk about doing proofs. Do you want me to? Yes? So if you want to go, feel free, but I'll keep talking since at least one person said yes. So I'll give you a couple of minutes if you want to scarf it. I do note that if you do want to know more about proofs, yes?
When are you going to go back to the subspaces?
Yes, proofs about subspaces.
Oh, okay.
That's where I was going to go back to. Cool. Thank you for reminding me. But that's what I'm going back to. There are some video worked examples on proving that things are subspaces on the Maths 1A page where this video will be as well, so feel free to look at them. Okay. That's maths learning. And I'm David. Okay, so after that little intermission, proving with subspaces. Okay, so interestingly, the last couple of years of exams haven't asked you to prove that things are subspaces, but there's no time like the present. Who knows? It might happen. I have not seen your exam. I have no involvement in your exam, so I can't tell you what's in it and what's not in it. And even if I was your lecturer, I probably wouldn't be allowed to. So I can't guarantee whether there will be a proof in it or not. In the last several years, there haven't been any proofs. Which makes me think that because it was such an important part of the course that it might come back, and knowing your lecturer, I would feel that there might be. Okay, just knowing David himself, that would be important to him. Okay, but he's not the only person who has control over your exam. The first year coordinator does veto questions sometimes, so I have no idea. But there might be proofs, and anyway, there definitely will be proofs about subspaces in the Maths 1B exam, because they're much more interested in proofs in Maths 1B than they are in Maths 1A. So we might as well cover it now. So, what I gave you before was a list of things that are subspaces and things that aren't, so that you could look at it and just know. Okay? But you are sometimes expected to have it there, and even though you can look at it and just know that it is a subspace, you're asked to formally prove that it really is. And that means it's not sufficient to just say it's a span, therefore it's a subspace, because they want you to basically do the proof that spans are subspaces. Okay, so the proofs all have a similar structure because it's to do with the definition of subspace. So the proof is structured by the definition of subspace because all proofs must use the definition somewhere, at least once. Okay, otherwise it's not a proof, it's just an explanation. Okay, so proofs have to use the definition, and the definition of subspace has three aspects to it, and therefore your proof will have three aspects to it as well. All right. Let me pull out that definition of subspace again. So we've got 1, 0 is in the subspace. 2, if V is in S and K is a real number, then KV is in S. And 3, if U and V are in S, then U plus V is in S. So before we even get to doing proofs, it's good to know what a proof would normally look like. Okay? So proving anything, there's only a small number of types of statements that you can possibly prove. Okay, so since there are 3 separate bits, I'm going to really have to do 3 separate proofs. Okay, a proof for proving that something is a subspace has 3 separate proofs within it because of the 3 parts there. Okay, so let's just think about this. So I'm going to count something, this symbol. Here I've made the statement that the 0 vector is in S. So S being a set, there is a rule that tells you whether things are in or out. In order to tell whether the 0 vector is in the set, I'm going to have to use that rule, because that's what that rule is for telling if things are in the set. So I'm going to have to show that 0 satisfies the rule for being in S. Here, V is in S. I know to begin with that V is in S, because it says if I'm allowed to, it says assume that V is in S. But therefore, because it's in S, it must satisfy the rule. So I'm going to use the rule for being in the subspace another time here. K is in R, that doesn't really count. KV will have to be in S too, which means that I will need to arrange for whatever KV is to satisfy the rule for being in S. U and V have to be in S, and U plus V has to be in S. So in total, 1, 2, 3, 4, 5, 6. There are 6 times in your proof where you will use the definition of what it means to be in the set that you are considering. So the set that you have has a rule for being in it, and you will have to use that rule 6 times, because it's 6 times in the definition. Okay? So that's just useful to know that that rule of being in a set will keep coming back in your proof. Okay. Now the final piece of information is that in anything where you have an if-then statement, the proof will always look a certain way. So if you want to prove an if-then statement, you will say, suppose this, and then there will be some working, and you will say, therefore this. Okay, and we'll say, suppose U and V are in S, working, 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 therefore U plus V is in S. All proofs of if-then statements look like that. Okay, some of them don't. Some of them says, well, actually first we'll just say, well, we'll just turn it into an equivalent statement and do it backwards of saying, well, maybe we'll say, if not this, then not this. There's some things you can do, and you can do it by contradiction, for example. But your classic if-then proof says, suppose the if, and then therefore the then. So now we know what the proof is going to look like, and all subspace proofs will look like this. It will feel different depending on what the definition of your set is like. So if it's a construction definition, your proof will feel a bit different than if it's an equation definition, because you'll have to do different kinds of working in the middle, but the structure of the proof will be the same. So let me do an example. I'll need 3 of them just to make it hard for myself. Okay, so I have the set, the 2 equations are x plus y equals 0, x minus 2y plus 3z equals 0. I'll write them bigger in a minute. Prove that that is a subspace of R3. Now I know that it is a subspace of R3 because it's got homogeneous linear equations. If it wasn't that, then it wouldn't be possible to prove that it's a subspace. So if they have a typo in your exam in such a way that it's not possible, you should tell them. Okay, but it probably won't happen. But I know that it's worth trying to prove it's a subspace because I know in advance that it really is one. Okay. So here's how the proof will go. Okay, so first I'm just going to write down the rule for being in S is that x, y, z must satisfy x plus y equals 0 and x minus 2y plus 3z equals 0. We do not need to write that down on our working, but it's what's going to be focused on. We're going to use that rule 6 times in our proof. So we must prove the 3 rules of subspaces. So law number 1 for subspaces is that the 0 vector has to be in S. So I'm supposed to do some working and conclude, therefore, the 0 vector is in S. And I need to fill in some working here. That's what I'm aiming to achieve. So, well, the rule for being in S, according to this, is that the coordinates have to satisfy these equations. So if the coordinates of 0 satisfy those equations, then it will be in there. So I have that 0 plus 0 is 0, and 0 minus 2 times 0 plus 3 times 0 is in fact 0, and so therefore 0 is in S. That's always the easiest one. Okay, because it satisfies the rule for being in S. 2. Law number 2 for subspaces says if V is in S and K is in R, then KV is in S. And so that as a proof will look like this. Suppose V is in S and K is in R. And then I will do some working, and at the end of that working I will say KV is in S. That's what the proof will look like. And I need to fill in working. But I have written a statement that V is in S, and I have a rule for what that means. It means that whatever the coordinates of V are will have to satisfy the equations, because that's what the rule is. The rule says to be in S, I have to satisfy the equations. So that means that I need to know what the coordinates of V are. So I will say let V be equal to X. I'll use A, B, and C. B and C. Then we know that if we sub that into the equations, it'll work. So A plus B equals 0, because we sub that into X plus Y, and A minus 2B plus 3C equals 0. So we have used the rule for being in S another time. So that's 2 so far. KV is in S. Well, the way of telling whether KV is in S is if we sub that into the formulas, it should both come out to 0, right? Because that's the rule for being in S. So in order to know whether it will work, we have to figure out what KV's coordinates are, because we have to sub them into the equations. So now KV must be KA, KB, KC. And if I sub them into the equations, I want them to come out to 0. So let's see. KA plus KB. This is supposed to come out to 0. Well, that's okay, because if I factorise the K out, I'll get Ka plus B. And we just said that A plus B was 0. So this one comes out as 0. And if I sub it into the other equation, Ka minus 2 Kb plus 3 Kc. Well, if I factorise the K out, I'll have A minus 2B plus 3C. And I just said that A minus 2B plus 3C is 0. So this is K times 0, which is 0. And so therefore, because it satisfies both equations, which is the rule for being in S, it must be in S. So we've now used the rule 3 times, got 3 more times. Isn't it nice that rule number 1 uses that law number 1 uses the subspace rule once, law number 2 uses the subspace rule twice, and law number 3 uses the subspace rule 3 times. Kind of cool, isn't it? I did not plan that, but it's just a happy coincidence. So suppose U and V are in S. Okay, that's how the next rule starts. It says if U and V are in S, then U plus V is in S. So my proof will say suppose U, V are in S, then therefore U plus V is in S. So again, this statement here is 2 statements. It's the statement that U is in S and the statement that V is in S. And when we go look at the rule for being in S, we have to know the coordinates to use the rule, so we'll have to give them coordinates. Okay, so let U be equal to like A, B, C, and V be equal to D, E, F. And then because of the rule for being in S, if I sub them into the equations, it'll work. So I'll get A plus B equals 0, and A minus 2B plus 3C equals 0. And I'll have D plus E equals 0, and D minus 2E plus 3F equals 0. And I know that those are true because I started with the fact that they are in S. So now I have used the rule another time. I've got 2 more to go. I've used it twice actually, once for U and once for V. I've only got 1 to go. And that will be down here, because to show that U plus V is in S, I will have to use the rule 1 more time. And to use the rule, my rule uses coordinates, so U plus V, I have to figure out what its coordinates are. So now u plus v is a plus d, b plus e, c plus f. And then in order to use the rule was that I have to sub the coordinates into the formulas, so I will do that. So a plus d is the x coordinate, plus b plus e is the y coordinate. Now let's see. I know that a plus b is 0, and I've got an a plus b. Okay, so if I just rearrange it like this, I'll get 0 plus 0, which is 0. And then I can also say the x coordinate minus 2 of the y coordinate plus 3 of the z coordinate. Now if I expand that out, I'll have a plus d minus 2b minus 2c plus 3c plus 3f. So I'll have a plus a minus 2b plus 3c and d minus 2. That's an e, isn't it? No. That's an e there, sorry. D minus 2e plus 3f. And I just said earlier that a plus minus 2b plus 3c was 0, and this is 0, so that's 0, and therefore u plus v is in S, because it satisfies both of the equations. And so, therefore I have finished my proof. So, since all conditions are satisfied, S is a subspace of whatever it was a subspace of, and I think since it has 3 coordinates in its vectors, it's in R3. That's how subspace proof works. And they will all work that way, and I will do another one before I fall over and show you one more, because then I'm going to have to stop and talk to the Maths 1Bs. Okay, so another example. Okay, prove that R plus S minus R, S plus R, where S and R and in R is a subspace of R3. Well, first let's just check if it's worth proving. Yes, I can rearrange that to look like a span, so yes, it is a subspace. Okay, so that's good. It might be helpful for me to rewrite it as a span to do my proof, but it's not actually necessary. It's not actually necessary to rewrite it as a span, but it might make my work easier if I do. So first I'm just going to say that, so I've got 1R, minus 1Rs and 1R, and I've got 1S and no S's and 1S. So actually it's a plane by the look of it, because it's got dimension 2, because it's got 2 free variables. It's got a basis of 2. Okay, so I'm just going to leave it like that because that's easier going to make my working easier, because I know that having less R's and S's in it is just going to make it easier. Okay, so I know it's a span because I can rewrite it as, I know it's a span and therefore a subspace. So my proof is going to work like this. 1, I need to say something that allows me to say that 0 is in S. So what's my rule for being in S? My rule for being in S is this. My rule for being in S is that it must be possible to write my vector in that form. So I have to write my vectors to look like that, and if they can look like that, they must be in S. And so, to write S in that form, 0 is 0 lots of 1 minus 1, 1, plus 0 lots of 1, 0, 1, and therefore it's in S. Because it looks the right way, because that's the rule. The next part of the proof says I will always begin. Suppose did I use V, did I? Doesn't matter. Suppose V is in S and K is in R. And then I'll get to the bottom and I'll be able to say, therefore, KV is in S. It will look the same as it did last time. I have to use my rule twice, so I need to use the rule up here to say that V is in S. That's saying that whatever V is, it has to be able to be written this way. So therefore, to be in S, V must be equal to that. So let's see. So V must be it must be R plus S for some, S and T, for some R and S. If I was being careful, I would probably use different letters, like A and B, and I might do that just so that I don't get confused with the original R and S, because I've chosen my own values for them that match the vector I actually have. Okay, I know that I can write it that way, because that's the rule for being in S. And my aim is to write KV in the same way. So let's figure out what KV is. KV is KA 1 minus 1, 1. So I'll times that by K. And if I expand that out, I'll get KA lots of 1 minus 1, 1 plus KB lots of 1, 0, 1. Which is in the correct form. It's something times 1 minus 1, 1 and something times 1, 0, 1, and so therefore KV is an S. Three. Suppose U and V are both in S, and at the end of my working, I'm supposed to get to, I don't know if I have enough room. I probably will. Let's just hope that I will. Therefore, U plus V is in S. Okay, so I need to use my rule. The rule for U being in S would be that U would be able to be written like this for some choices of R and S. So therefore I can say, so U is something times 1 minus 1, 1 plus something times 1, 0, 1, and V is something times 1 minus 1, 1 plus something else times 1, 0, 1. You have to use different letters for the two of them because they could be different vectors, so they might have their own R's and S's, R's and T, whatever they are. Okay, and then U plus V, well, if I add them together, I'll have A plus C lots of that vector. If I add them together, I'll have B plus D lots of that vector. And therefore, U plus V is an S because it's something times 1 minus 1, 1 plus something times 1, 0, 1. That's how subspace proof works. There are still more situations you could be in. One of them is the matrix version, where you've got your subspace written totally in algebra with no numbers at all. And I will do that. Will only take me a couple of minutes, so I might as well do that one as well. And this one's actually in your lecture notes. Let A be a matrix, and let S be equal to the set of x's in Rn such that Ax equals 0. So technically it would be a matrix that's sort of, m by n. Okay, so this one's written a little differently to the way I talked about things, but it's still the same. We just haven't specified the actual coordinates. I've still got, here is where to look to find the vectors that are supposed to be there, and here is my rule for being in S. I have to sub my coordinates into that matrix equation, and it should come out to the 0 vector, and then it will be in the subspace. So I'm going to have to use that rule, however many times the rule is used. 6. So prove S is a subspace. This one's actually in your lectures. It was embedded in a list of examples of subspaces. Okay, so rule number 1, I will have to say therefore 0 is an S. So I need to do some working. The rule for 0 being an S would be that if I put it in the spot of X, it will come out as 0. So A times the 0 vector, because I need to put it, the X is this 0, does in fact come out to 0, tick, so therefore 0 is an S. Suppose V is an S and K is in R. Okay, and my final statement will have to be therefore KV is an S, because that's what my proof must look like, because that's what I'm trying to prove. And now, what is the rule for K being an S? Sorry, V being an S? Well, that would mean that V in this spot will make it come out to 0, because if I sub V into that formula, it will come out to 0, because that's the rule. So AV equals 0. And what would be the rule for KV being an S? Well, that would mean that A times that vector should come out to 0. So let's see. A times KV, and I need to do some working to convince the reader that this comes out to 0. But I could bring that constant out the front, because that's how constants work in matrix multiplication. So that would be K lots of AV. But AV was 0, because just from there, so this is 0, and so therefore KV is an S. Because when I sub it into that formula, it comes out to 0, and that is the rule for being an S. Okay? Well, the rule for U being an S would be that U would go in the spot of X and it would come out to 0. And the rule for V being an S would be that V would go in the spot of X and it would come out to 0. And then what I want is for U plus V to satisfy that same equation, because that's the rule for that being an S. So U plus V. And we need to attempt to use these two bits of information. I'll expand it out. Expanding out is always a good plan if you don't know what to do. And I was just said that AU is 0, and I just said that AV is 0. And so therefore this is 0, and therefore U plus V is in S. Therefore S is a subspace of Rn. Same structure. This is actually in the satisfying equation variety, but there were no numbers anywhere. It was all algebra, and they all work the same. That's proving that things are subspaces. Right, well, thank you very much. I really have to stop now because I should eat lunch before I talk to the Maths 1Bs. Good luck in your exam. Maths Learning Centre is open next week, and I've put like heaps of staff on, so we should be able to help you out. But I do ask you, please, try and sit with other people who are also doing Maths 1A, because you'll study better. Thanks. Sorry? Maths 1B this afternoon. I might have written it wrong, I'm sorry.